Hey everyone, and welcome. Today, we're going to break down two ideas that honestly make our entire digital world tick: parallel and distributed computing. So let's jump right in and see how we create the incredible power needed for everything from your phone to massive data centers. It all boils down to this one simple but really big question. As the amount of data we have explodes and the things we want to compute get more and more complex, we eventually just hit a wall. So what do you do when a single computer, no matter how powerful you make it, just can't keep up anymore? To really get the solutions, we first have to understand the starting point, right? We need to look at the traditional way of doing things and see why it has its limits. And that brings us to centralized computing. So what exactly is centralized computing? Well, in a nutshell, it's an architecture where pretty much everything happens in one spot. All the heavy lifting, all the processing, the storage, the day-to-day management, it's all handled by one main server. The key takeaway here is that you have a single point of control for the whole operation. A really great way to picture this is that classic client-server setup. Just imagine one huge, powerful mainframe, the central brain, and then you've got a whole bunch of simpler computers or terminals that connect to it to get any real work done. All the smarts, all the power, it all lives right there in the center. So once that central brain starts to max out, we need a new game plan. This is where we get to the two main solutions that really form the foundation of almost all modern high-performance computing: parallel systems and distributed systems. Okay, first up, let's talk about parallel computing. The whole goal here is to make a single computer faster, but from the inside. So instead of having one processor chugging along doing one thing at a time, you have multiple processors, or cores, all working on different tasks at the exact same time, all inside the same box. That concurrency is what saves a ton of time and makes your computer feel snappy. And what's so cool about this is that you're using it every single day, probably without even thinking about it. That multi-core processor inside your laptop, your desktop, even the phone in your pocket, that is a perfect real-world example of parallel computing. It's exactly how your device can stream music, download updates in the background, and let you scroll through a web page, all at once without breaking a sweat. All right, now let's flip the coin and look at distributed computing. This approach is totally different. Instead of trying to beef up one single computer, we connect a bunch of separate, independent computers over a network and get them to work together on a problem. And to you, the user, it just looks like one single massive system. But here's the absolute key. There's no shared memory. These machines have to talk to each other by passing messages back and forth. This table lays out the differences perfectly. So with parallel computing, you're on a single computer. With distributed, you're using multiple computers. For memory, parallel systems can share it, which is super fast, but in distributed systems, it's always separate. Each machine has its own. Communication is another huge difference. Parallel systems use a super fast internal bus, while distributed systems have to send messages over a network, which is slower. And maybe most importantly, their goals are different. Parallel computing is all about squeezing out every last drop of performance. Distributed computing, on the other hand, is built for scalability and fault tolerance, meaning it's easy to grow and it can keep on running even if one of its computers fails. Okay, so now let's dive a little deeper into that distributed world, because it's not just one single thing. It's more like a whole family of different models, and each one has its own personality and its own best uses. We can pretty much break down these systems into four main flavors. We've got clusters, computing grids, peer-to-peer or P2P systems, and of course the one everyone's heard of, cloud computing. Let's do a quick run-through of each. First on the list, clusters. The best way to think of a cluster is like a highly trained, uniform team, like an Olympic rowing crew. It's a group of identical computers. We're talking the same hardware, the same operating system, all connected together and working as one single unit. And there's usually a central scheduler doling out the work, which makes them awesome for really heavy, predictable jobs. Next up, we have computing grids. Now, if a cluster is a uniform team, a grid is more like a giant, diverse, global volunteer project. These systems are loosely connected and decentralized, and the computers are heterogeneous, which is a fancy way of saying they can all be different. Different hardware, different operating systems, you name it. Grids are designed to link up not just computers, but also software, scientific tools, and even people, often across huge distances. Then you've got peer-to-peer, or P2P. This is the most democratic, almost rebellious model of the bunch. In a P2P network, every machine is an equal. It's both a client asking for things and a server providing them. There's no central boss, no single point of control.
The whole system organizes itself, and computers can join in or drop out whenever they feel like it. The classic file-sharing networks? Yep, that's P2P in its prime.
And finally, cloud computing. You can really think of the cloud as an evolution that takes the best ideas from clusters and grids, virtualizes everything, and then packages it all up into a super easy-to-use on-demand service. It gives us this massive pool of resources that anyone can tap into to get their apps up and running and scaled in minutes, handling everything from huge background jobs to the apps you use on your phone every day.
So we have all these incredibly powerful and complex systems. But how do we actually know if they're any good? How do we measure if they're performing well? What are the yardsticks we use to see how efficient they are?
Well, there are a few really important ones. First is system throughput. That's basically how much work the system can get done over a period of time. We measure this in things like MIPS, or millions of instructions per second, or for the supercomputers, T-flops. That's trillions of floating point operations per second. Just a mind-boggling number. We also care about job response time, how long you have to wait for a single task to finish, and network latency, which is the delay as data zips across the network. And finally, there's system overhead, which is all the time the system spends on housekeeping tasks instead of on your actual work. You know, building one of these systems is one thing, but making it grow bigger and handle more work without falling over, that is a whole other challenge. And this is the critical concept of scalability. And scalability isn't just one simple idea. It's got a few different dimensions. There's size scalability. That's the obvious one, just adding more processors or machines. But there's also software scalability, which is about making sure the operating system can handle all those machines. Application scalability, which means your program has to be smart enough to actually use all that extra power. And finally, technology scalability, being able to adapt to new and better hardware as it comes out. This slide gives you a jaw-dropping picture of size scalability. Just look at this. In 1997, a top-of-the-line IBM system could handle about 512 processors. Pretty good for the time. But fast forward just over a decade, and the Blue Gene/L supercomputer could scale up to an incredible 65,000 processors. That's not just an improvement, it's a complete change in what's even possible. But scaling with new technology is way more complicated than just numbers. It's not as simple as swapping in a faster chip. You've got to think about time. How do new generations of hardware affect the whole system? You've got to worry about space, the actual physical size, how to package it all, and, a huge one, how much energy it's going to consume. And then there's heterogeneity, the massive headache of trying to get parts and software from dozens of different companies to all play nicely together. So from that single central brain all the way to globe-spanning clouds of computers, we've seen how computing has had to evolve to meet these insane demands. It really leaves us with a big question, doesn't it? As our world gets more connected and as we create more data every single day, which of these models, or maybe some new combination of them,